Okay, this is chapter 2, part 3. We left off last time talking about the difference between, remember the dots on a scatter plot, the distance between any of those uh, dots, and the line, the model line, which attempts to summarize those that scatter plot, the sort of spread of those dots, which each one of those dots represents where a person falls on the graph, right? Well, we call that error the gap between the dot and the line, straight down or straight up to the model line. Deviance is another word for that error. That means the difference between the value predicted by the model and the actual observed value. So an example of that is your model is mean height 56 inches, but person A is 58 inches. So the deviance is 2 inches. See, so a really simple model would be simply to say, well, we're going to predict your individual height based on the uh, average of the height for the group. That's really the simplest model. As we could say, well, we don't have any line any fancier or any more precise than just the mean. And so we take a sample of, say, a class, and we measure everybody's height in inches, and we find that the average is, say, like 65 inches or something like that. You know, say it's like 5 feet 5 for the class. So we could say, okay, we know that the average is 5 feet 5. So if we're trying to predict what the height is for you, an individual in that class, we don't know any better. The best we could do is say, well, you're probably average. Most people are close to average. So we're going to guess that you're 5 foot 5. But we're probably going to be off a little bit. You'll be a little taller, a little bit shorter than that. And that's the error of the deviance we're talking about. Now, this visual that you see here is this sort of thing, but it's actually a different example that I take straight from your textbook. And here you see on the x-axis you have what looks to be 5 different lecturers, lecturer 1 through all the way lecturer 5. And on the y-axis you have the number of friends that each one of those professors has. So you take this little group of professors and you come up with an average. You say, well, the average, the mean for this group is somewhere between 2 and 3 friends. You can see on the y-axis there the 2 friends, 3 friends, and the line here, that's the mean, the average, is somewhere like a little over 2.5 friends per person. That's the average. So we draw a line, and that is our model line in this very simple situation. We're just saying, okay, we're just going to say that our line is the mean, and we're going to predict everybody has an average number of friends, 2 point whatever that is, 2.6 friends. But look at how each lecturer has actually a little bit more or a little bit fewer friends than the average. So a lecturer number 1 here only has 1 friend. And so he or she, their deviant score is 1.6 because there's 1.6 units between their actual number of friends and what the model, the mean, predicts their number of friends would be, 2.6 or whatever that number, whatever that line is. You can't tell exactly. But that person is 1.6 friends lower than the average, than what is predicted for anybody in this sample. And you can see here that lecturer number 2 has got 2 friends, and so he or she is 0.6 points below the prediction line, the average for the class, or not the class, the sample. And you see this lecturer has 3 friends, and this lecturer has 3 friends. So they're a little above the prediction line. They have more than predicted. And so again, the gap, the distance between what they actually have, friends that they actually have, and what's predicted for them, that's their deviant scores. Each one of these scores that you see listed here, that's the deviant score. It's the error, the difference between what we predict for each person and what they actually the value they actually were given. That's just a fancy way of saying the number of friends that they actually have. So these two lecturers each have 3 friends. This lecturer has 4 friends. And so he or she is 1.4 points above the prediction, above the average for the sample. And so we're under predicting this person's number of friends. So again, just to repeat, each one of these is a deviant score or an error score. There's just 2 different words meaning the same thing. And if you want to know what the total error is, you can see this equation up here, that the total error for this sample of 5 lecturers is if you take and add up all of these individual deviances, you add them all up, that's what this is indicating here. And so since some of them are negative and some of them are positive, and they're all sort of surrounding the mean, they end up canceling each other out and you get 0. So that's what you would expect when you're taking the mean and then looking to, adding up all the people who are below the mean and above the mean, you end up getting 0 error, because all the error cancels out. You get some people who we predict too high, some people we predict too low for, but you add all that up and it all cancels out and you get 0 error. So that's one thing that that happens in statistics, is that the error, if it tends to get canceled out, especially if you have lots and lots of people in your sample, you're going to predict some too high for some people and too low for other people, but it tends to cancel itself out so that your prediction is kind of in the neighborhood of it's fairly accurate. That's the idea there. Okay, here you see the same thing with just another example that I pulled this picture, and here you have height and weight. And so each one of those dots in this example is how tall the person is, that's the height on the x-axis, versus how heavy everybody is, that's on the y-axis. And each one of those points represents one person. And then you have the model line that cuts through the middle of all those dots. And then you see how some of the dots are above the line, some of the dots are below the line. Those are the deviants. That's the deviance, the distance. Those straight vertical lines that you see, that's the distance from the dot to the line. That's the deviance or the error. Because again, just to reiterate, to drive this home, that your model is not going to perfectly predict what you're trying to predict, because, as I said last time in the last section, the humans are complicated, and just because there's a correlation with this example between how tall you are and how much you weigh, taller people tend to be heavier. But that's only a tendency, because some people might be really tall but really skinny, and some people might be really short and really heavy. So it's only a correlation between height and weight, and you can see that that's certainly true, that there's these people who are mapped out on the scatter plot. Some of them are higher than the line, some of them are lower than the line. So even though they're not too tall, they might be pretty high in weight, and they might be kind of tall but end up being kind of low in weight because they're really thin. So that's just another example to drive home some of these points that we're making. Okay, we want to know how much total error there is in the model. There's a statistic which I'm not going to get into right now. A lot of these statistics in this course, I'm not going to go over the equation and work through the equation and have you folks do exercises where you're actually doing computations with equations. And the reason for that is we're limited in the amount of time we have at this course. And to me, we have to prioritize. And so what I want you to be able to do, my goal for you, is that you can learn what you need to learn this semester to go out and do a project, an actual data analysis project, if you need to, whether it be for a thesis or for some class project or whatever. If you go forward to get a PhD and you need to do a dissertation or have a research agenda and conduct studies, well, I want you to have the skills to be able to do that. And one thing that you honestly don't absolutely have to have is a memorization of these equations. and the ability to by hand go through and do an exercise, do problems where you're plugging numbers into these equations and all that kind of thing. I'm going to teach you the practical stuff that you need to know to be able to go out and actually do this stuff. And the truth is, we let the software, whatever computer you're using, the software to calculate these statistics, so you don't have to do them yourself by hand. They're cumbersome and difficult to do by hand anyway, especially in a real world situation. So anyway, just remember for now that there's this statistic that's called mean squared error that gives you a number that will tell you how much total error there is. And this will be an indication of goodness of fit, because if you have a really big number, then that's an indication that your model's not very good. Your dots are all over the place and not close to your line. If you have a really good goodness of fit, then your dots are going to be close to that model line, and they're not going to depart. You're going to have small little deviances, small little distances from those dots to the line. And that means good. That's good. A strong goodness of fit. Your line fits your data very well. Now, if you're paying attention here, you might be saying, "But Professor, you showed us just a moment ago. You showed us a moment ago that back to this slide here, that all the deviances, the errors, added up to 0. So what are you talking about? How this mean squared error statistic, if it's bigger, it means that your model's not so good, and if it's smaller, it means that your model is better, that you have better goodness of fit. What's going on there? Well, what they do is, we don't get into the mechanics of it too much, but what they do is this. You notice that said mean squared error. So what you do is, if you square these deviances, negative 1.6, negative 0.6, etc., you square those numbers and they all become positive, because you know that a negative number times itself times another negative number is a positive number. So all the negatives here, the negative 1.6, the negative 0.6, it turns into positive numbers. So when you add all these squared numbers together, they're all positive, and you're not going to end up with 0. It's going to be a positive number. And the bigger those squared deviances, the bigger your error is going to be. So the way they get around this cancellation problem that I talked about before, where negatives cancel out the positives, is you square everything, and then everything turns positive, and you don't have negatives canceling out positives. Everything's positive now. Okay, so that's how they get around the problem of cancellation, by squaring everything. And if you recall back from an earlier course where you might have gone through and calculated standard deviation, if you remember that, the calculation of standard deviation requires squaring for the same reason, is that you have to get rid of the negatives so that the negatives don't cancel out the positives, and you end up with a 0. So squaring is a technique around that problem. But again, all I want you to understand for right now is this conceptual idea that we have a statistic that can tell us how much error, total error, there is in the model. In other words, how bad our model is. If there's more error, it's a worse model, right? Less error, better goodness of fit. We have to estimate population parameters using only samples, and samples are imperfect representations of population. So statistics from the sample are likely to be a little off from the true population parameter. I drove that home last time. But it's certainly true that statistics is not some sort of perfect science where you are always accurate. You're trying to project from a little sample what your entire population looks like, and that is an imperfect process. There's there's this error element in here, this imprecision, this lack of accuracy, and so that's why we call these statistics that come from your sample, that's why I call them estimates. We want them to be as precise and accurate as possible, but we understand from the get-go that they're not going to be perfect. Now, sampling variation. If you were to take multiple samples from a population, you're likely to get somewhat different results each time. So this only makes sense that, think about it, since there is a certain element of randomness, of sort of accidental error. If let's go back to that ISU example that I used earlier. If we want to get people's attitudes on their favorite format for classes, um, online, in class, etc., and we don't have time to talk to the 10,000 plus students on campus, but we can talk. We have time and resources to talk to 100 of them. So we grab 100 random students and we ask, okay, what's your favorite type of course, format-wise, online or in class, etc. And so we'll get a number for the sample. Let's say that you get 40% who say, you know what, I honestly like fully online courses. It's very convenient, it's straightforward. I can do it whenever I have time. I like them fully online. And with recorded lectures like this, that's the way I like it. So you get 40% that say that with this first sample. Well, we don't normally do this, but imagine a situation where we go out and get a second sample. And due to just the accident, the sort of, you know, the accidental random error that you're going to get when you do statistics, we grab a fresh 100 random students, we calculate their attitudes about favorite class, and this time 44% of the students say that their favorite course is online, an online course. And then let's take a third random sample of 100 students, and maybe this time they'll say 38% say that that's their favorite course. So it's all kind of around 40%, but sometimes less, sometimes more, and you get variation. That's what we mean by sampling variation, is that it is going to vary from sample to sample to sample, because this is not some sort of mathematical certainty where everything is the same every time you do it. There's going to be some variation there. Now, we're far enough into this video that I'm going to go ahead and pause here and continue this discussion of sampling variation, what that means for us and what we need to be aware of. And I'll do that in the next part. We'll see you there.